Yeah, so I wanted to give a talk about embedded programming. Before I really got into functional programming, that's what I did as a full-time job. A lot of C programming and a lot of memory manipulation, and it's really interesting when you move into functional programming how nobody cares about any of that stuff. And it's great, but I always miss it whenever I have to go back and do embedded programming still at my current job. I sort of miss the ability to have functional things, which is what makes ATS so interesting, is it's an attempt to try and bridge those two things, allowing you to have like low-level details with a functional language, and a lot of other stuff thrown in. Oh, good. We'll just kick this off nicely. Okay. So, basically, the end goal of this is the little box that's sitting in front of me has two blinking lights. So we're going to do a whole bunch of stuff to make two blinking lights happen. Probably more stuff than you've ever seen happen to make two blinking lights happen. All right, so the first thing I wanted to talk about is what functional programming means to embedded developers. And it's pretty simple. You see right there? That's the function. So this is functional programming because I'm using this function. Very clear. So this was my point of view when I did embedded development. Functional programming was using functions. Of course, now that I actually know what functional programming means, it's a lot more than just the fact that you use functions. In fact, it's the idea that everything you're doing is functions. But most people who do embedded, they're not concerned about that. They have their own problems, which I'll get to. So on the other side, this is what embedded development means to a functional programmer. It's clearly embedded. I have only 16 gigs of RAM, so I don't even know how I'm supposed to get anything done. And it's in a truck, so that's embedded. All right, so, but what, I wanted to talk a little bit about these terms, because it's usually a good place to get started. So what does embedded mean? Well, to me, what it means is that you're constrained in two ways. The first is you're constrained in the way you can interact with your environment. And the second is you're constrained in terms of what resources you have. So that's, the second one has changed over time, right? Like what resources you have and what qualifies as embedded versus non-embedded has changed a lot over the years. The first one really hasn't. You know, the way you interact with the device is very different in an embedded system. It's going to be lights, and it's going to be, you know, smaller screens, or maybe no lights at all, maybe just motors and handles and things like that. Okay, so like I said, yeah, here's some examples of constrained input and output, right? So you have a solenoid here, or a pressure transducer here, and a stepper motor, and some LEDs, and even an iPhone, which is a very, very, you know, rich user interface. In a lot of ways, it's still constrained relative to a desktop and what you can do with a desktop computer. Yeah, and so this is a nice, talking about resource constraint. This is where I think of embedded now. So, you know, a long time ago it was kilohertz, not megahertz, but now I'd say it's megahertz, not gigahertz, megabytes, not gigabytes. For disk space, megabytes, not terabytes, right? So again, this is all moving targets. When I first started with embedded programming, it was kilohertz, not megahertz, and you know, a megabyte was a lot. Like that was, you were doing great. But now, you know, you can get a Raspberry Pi and get a gig of RAM, so. Yeah, and speaking of which, you know, a lot of times there's a tendency to talk about embedded, and embedded means you're using an ARM. Well, that world's changing really fast. Here's some benchmarks. You can see there's plenty of applications where ARM is just a little bit behind where we are with x86 processors. So that world's changing too. It's just kind of a nice graph to see how fast things are happening, and things are always changing in this space, and what counts as embedded and what doesn't. Another element of embedded system is they're often the most important systems in the world. And it's kind of ironic when you think of the amount of safety that goes into developing a web app in terms of test-driven design, or, you know, type safety in case of functional programmers. But a lot of work goes into making those systems very safe. I mean, I'll tell you from experience, not nearly as much effort goes into making, say, a water treatment system safe. You know, it's very much up to the programmer, and there's not a lot of tooling that helps you. So, you know, when we're looking at this programming language that I'm going to show you, and you're going to see that it seems a lot more complicated than just writing raw C, for instance. keep that in mind. We're trying to target a world that has very important constraints. Okay, so now let's talk a little bit about FP. Like, what are some of the things that we'd want in FP? So to me, some of the most important properties are that functional programming is nice to reason about. It's verbs, not nouns. That's what I'll tell people when they're first coming into it that are used to, say, Java or C++. So you're talking about, you don't say, blink class dot execute blink. Instead, you just say blink, and then you tell what you want to blink. So that's a very nice feature. It's also nice to reason about because there doesn't tend to be as much going on behind the scenes that you don't see in the code you're looking at. It's a really important property. It's sort of referred to as referential transparency, but I really mean sort of more soft than that. Like, it just tends to be that you can tell what's going on by looking at a page of code. Immutability is another wonderful feature, and I'll kind of go through each of these in a little bit more depth here in a minute, but immutability and composition too, the ability to build programs up from smaller pieces. Those are the things that functional programming advertises, and I feel like they're important in any computational environment, not just the places where it's become more popular, like, high bandwidth data environments, for instance. So yeah, a little bit about reasoning about functions. I think this is a really good example of, you could show this to almost anyone who knew what a greater than sign was, and they have a pretty decent idea of what's happening, Give me the bigger one, an X or a Y, whichever one's bigger, give me that one. It's just a lot cleaner to read. And you write a lot of functions that look like this. Functional programming gets a rap of having all these monads and like complicated things, but all that is to support being able to write functions that mostly look like this. And if you're doing it right, most of the time things should look something like this. Immutability. So like I said, I was going to come back to that. When you say x equals 3, it does. In other words, in an immutable world, variables have a much more mathematical definition. So you're not talking about a place in memory. Instead, you're talking about binding an expression to a name. To me, that's the key concept of immutability, is that you're binding an expression to a name, and then that name always means that. So being able to say that you've checked this register and now you have it, and then turning off the light and knowing that if you've done this right here, you don't have to worry about somebody else changing this out from under you, is an incredibly important property. Or changing the meaning of it in the same scope. Higher order functions are something that wasn't on my first slide, but higher order functions are something that you quickly grow to love if you're a functional programmer. Being able to map across your data using a set of functions, bringing your functions to your data instead of the other way around. So what do I mean by that? Well, here's some data, for instance, right? And then I want to set up some operations on that data. So I can start by writing this case like this, where I have something simple, and then I map over this. But let's say important numbers changes and it needs to grow bigger. Well, I can put that data somewhere else and make it bigger or change what it is, but my computation stays separated from it. It's probably the core difference between functional programming and object-oriented programming, is the idea of operational separation from data. Again, these are just really simple examples, but it's just to illustrate points. Composition's sort of on the same theme, right? So maybe I have one set of building blocks that I build one place, and somebody else has another set of building blocks they build, being able to compose them. So here we have division and addition, and they're composed together, and we can run them on our data. Again, the computations come to the data, which is really nice. One more thing we might want, type guarantees. Not strictly functional programming, but often closely associated with it, is the idea of really nice type guarantees. In this case, I have a register that's wrapping an int and a light that's wrapping an int. If you were going to write this without types, you'd have disable alert, and you'd have a variable named register and a variable named light, and it would produce a bool. But you could accidentally put the light in the register spot and the register in the light spot, and your function would be none the wiser until runtime. With types, you get that guarantee ahead of time. A register has to be a register, and a light has to be a light. It's a really nice property to have. And the more people, well, there's two schools of thought about types, but for a certain set of programmers, myself included as a high school programmer, that ability to define your data before anything actually happens is really nice. So that's what's called a static versus dynamic distinction. And types formally specify the static part of your code, the part that is there even when you're not actually running the code, the things you can know before you run it. Okay, so then, I feel like I made a pretty strong case for functional programming. And the question is, why aren't people doing this in embedded spaces? Why don't they do it where you have these problems where there's really a lot to offer? The world of embedded systems is a world of statically known things. You often know almost your entire system state before you run the program, but you won't see any of this stuff. And the question is why? Well, there's really good reasons. Embedded systems prioritize the machine. Remember, one of the things that we are is resource constrained. So all those fancy types and nice binding operations take a lot of memory, and they do a lot of tricks behind the scenes that you can't see. And that's just not acceptable in a lot of embedded applications. And most embedded programmers don't want to figure out if it is or isn't acceptable when they pick a programming language. They want to solve the problem. It's not just a matter of being able to say this is fast, right? So a lot of people associate it, well, functional programming is just not fast enough. But it's not just about fast. It's about knowing how much space is used. It's about when is memory allocated. When are you actually? So if I bind an expression to a variable, I say, oh, it's all like math. But we all know, like under the hood, somewhere memory is being used, and you have to know that when you're doing embedded programming. Timing of operations. Yeah, I have the vaguest inkling of when things actually happen in a Haskell program. It's lazy. It's not even, you don't even get to know that when your function is called, it's going to happen. Even in a strict world, you don't know when garbage collection is going to happen. You don't know what part of your code is going to be called and when. So, this is an example of something you might see in a more embedded space, right? So first of all, look at this type, uint8t. So you're explicitly talking about something machine related, 8. It's 8 bits. So we know exactly how many bits this has. Size of selectors, right? So that we're asking how many bytes does this selectors type take? And those are the kind of things you just never see in functional programming. It's not that they're not possible, but you never see them. Yeah, so I like to throw this in here. This is a memoized sine wave that'll be mapped into memory for a fast PWM counter. I would love to see somebody write this in Haskell. It would be really interesting and have the same kind of memory guarantees, because I know how I would do it. I would write it in C and import it into Haskell. So C, you've heard me mention C a few times. C is the language of embedded processing, and it's really great with the machine. It tells you all kinds of things. It's got some weird syntax at times, but once you learn to use it, for years I didn't understand why anybody wanted any other programming languages. I thought it was as good as it could get. But then I started to do more complicated stuff, and I realized there's some really good reasons. All those nice properties that we have in functional programming, we don't get any of those in C. And in fact, we create new problems for ourselves. Crazy macro expansion being a really common one. All these things are a problem. Reasoning about your program is really difficult. Algorithms are obfuscated. Tracking down how an algorithm works in C it's fun. It's an art. Invariants are not captured. What do I mean by invariants? I mean the fact that something in your code stays constant is really hard to discern in C. The fact that you have something that should be knowable at compile time. It's really hard to track that in C. Mistakes. I don't know. I think like every important security bug in the last few years seems to be related to some feature of the C language. The Spectre bugs maybe not, but Heartbleed definitely was. Okay, so here's the question. Can we have both? Can we have embedded systems, memory stuff? Can we analyze space? Can we have well-specified code, higher order functions? It's a lot to ask. ATS, ATS really does give you all these things. You have C-like memory control, and I mean C-like memory control. You can tell it exactly where to put things. You can talk about, particular memory addresses. You can talk about, the boot vectors, like really, really low-level stuff. C timing control, same thing. It's exactly like C. Higher order functions. I skipped borrow C compilers. Yeah, ATS cheats to do a lot of this. It actually is just using the exact same compilers. It compiles down to really nice C code. But higher order functions are there. You have some really nice higher order function stuff, including guarantees like really closer to AGDA than Haskell. Guarantees like termination can be added into ATS. Rich types, very rich types, we'll go into that. Refinement types, we'll go into that too. Linear types, theorem proving. Just curious, how many people have heard of linear types? Raise your hand. All right, we have one person. Good. Linear types are fun. And how many people have heard of the language Rust? More people. Okay, so linear types are a big deal in Rust, right? So that's how they give all their guarantees. ATS has those, so that's a fun one. What about refinement types? Raise your hand if you've heard of refinement types. All right, good deal. That they are neat too, and we'll get there. Oh boy, there's so much to do. All right. So, what's the catch, right? We've got a programming language that can do all these things. What's the catch? The catch is it's ridiculously difficult to program in. I mean, like, to the point that the whole time I'm writing this, I'm like, why? What? But I'll tell you why. Like, I don't think this is a programming language that people will use. I think it's the parent of the programming language people might use to write embedded systems. However, if you have an adventurous soul and you like the idea of getting lost in the weeds and digging through syntax, ATS is really interesting, and you'll learn a lot about how compilers work, and you'll learn a lot about how, types work, and many other things. Also, I want to say that I am not an ATS expert by any means. I am on this journey myself and often stumble, but I do enjoy it. Yeah, also, I mean, there's some serious hipster cred. Like, how many people had heard, raise your hand if you knew what ATS was before you walked in or heard about this talk. Yeah, don't feel bad. Like, if you check the user group, I think we might have broke 500 in the user group. That's the Google user group.
I work in the embedded space, and I thought you were talking about automated transfer switch.
Yeah, he said he works in embedded, and he thought he was talking about automated transfer switch, but it's applied type system is what that is. And this is actually ATS2, and ATS3 is on the way. It's a really interesting language. It's a research language, which means it's being actively worked on and developed, and features come and go, which is also fun. I started working with ATS a couple years ago, which is sad because I still don't know a lot of it. And it has changed a lot since then. It's gotten better. Like, every time it gets better. It's just, it's complicated. Anyway, hipster cred. So yeah. Is this even what hipsters look like anymore? I was wondering about that. Like, I found that picture, and I was like, I'm pretty sure that's, like, old. All right, let's write some code. Okay, so first, in this little box that's blinking, there is one of these guys. It's an Adafruit Circuit Lab, and if you're going to do embedded development, I recommend getting one because they're amazing. They have lights, accelerometers, buttons. They have lots of places you can tie in your own LEDs. They have switches, just everything you want. I'm going to use almost none of it. Instead, I'm just going to make a little light blink because that was really hard. I know, I hope I am. I hope everyone appreciates just how I think you should just jump in, have your company, just start using ATS right away. If you do that, please let me know. I would be so interested. Okay, so blink in C, right? So let's walk through this real fast. First, up here, we are initializing our I/O. So DDRC, does anybody program on an Atmel? Raise your hand. I know we have other people, but I'm going to ask the people here. Yeah. So some of this look familiar? Yeah, so DDRC is the data direction register. So for every one of those neat little pins, you have to tell whether you're going to be expecting voltage to be applied or you're going to be sending voltage out into the world, right? So a 1 means you're sending voltage out into the world. A 0 means you're not. If you mess that up, everything's going to work wrong. As you'll see, there's a lot of guarantees to make sure that you get it right. Oh, wait, there's absolutely no guarantees to make sure that you'll get it right at all. And you probably won't get it right, at least once you do something sufficiently complex. The blink, if you don't get the blink right, like, I mean, that's a bad world. So, you know, please bear in mind, like, all the examples I'm going to show you now don't really make sense for this blink example. Imagine a much more complicated project, preferably like a starship. So here we init our I/O, and we're now saying everything on port C, which is on our microcontroller, is going to be going out. And then what I do is on port C, we change the bit value of pin 7 to be high. We delay for 1,000 milliseconds, then we turn it off, then we delay for 1,000 milliseconds, and so on. Yeah, I mean, first of all, looking at this, very not functional programming, right? Like, you know, we're assigning to memory, everything's mutable, lots of side effects, all kinds of stuff. Also, pretty difficult to even see how you would do it functionally. I mean, like, you can do some bit manipulations, but doing bit manipulations on a port, it seems pretty rough. All right, let's change things. All right, before we change things, I want to talk a little bit about how ATS works. Okay, so, like I said, ATS is really difficult. Vanessa McHale is a person who's made it much easier. Last year, I guess, maybe she started working on an ATS package, and it's wonderful. It's kind of like a package manager for ATS, so you can actually make a package and run it with a single command instead of having to run make files and bring in everything yourself. And it works wonderfully. However, it does not work at all for embedded. So what I would suggest is learning ATS on your laptop with the ATS package system, and it'll be great, and then getting your make files out and going to work. The thing about embedded is, you know, amazingly, nobody's writing ATS to AVR compilers yet, so you have to use an intermediate compiler, and that's going to be a C compiler, and that's why you need the make files. And so then another thing, start with C and work out. So like I started here, I started with a blink in C. That's a really common way of like writing something in ATS when you're getting started. Okay, so these are different files that we're going to talk about. We have DATS files, CATS files, SATS files, and HATS files. It is not a Dr. Seuss book. This is going to be our main chain right here, right? So we take all these, I should have labeled that ATS compiler. This is an ATS compiler. You can tell by the plus. And then that's going to take it to AVR GCC, which is the GCC that gives you binaries. This puts those binaries onto this device here. It's a lot cleaner path if you're going to your desktop. You just run ATS package. Thank you again, Vanessa McHale. I don't know if she'll ever see this, but boy, I sure like ATS package. Okay, CATS files, named after cats. Not really. It's named because it's C code, right? So it's a way you can call C code. There's like 5 ways of calling C code. This is one of those ways. SATS files. SATS are for static ATS, I think. But that's what I'm going to say this for, because that's where you put your static stuff. So it's stuff you know at compile time. So you type definitions, function implementation definitions, external functions. So you have to know about where to find an external function at compile time, right? Yeah. Sort definitions. So a sort is a type of a type, basically. So you define sorts in ATS too. Why not? And then DATS files. DATS files are dynamic ATS, right? So this can be any of the other categories plus everything that can happen at runtime. So that's you know, really everything. All right. So first, like I said, we're going to do a little bit of C programming to get things started. And you might be like, well, this is cheating. This is exactly what you do in Haskell. But first of all, there are some notable differences. The first being that this is unbelievably usable in ATS in a way that it isn't usable in something like Haskell or Scala. Well, I shouldn't say or Scala. Maybe Scala has a much better FFI than I think. But these types are shared. between ATS and C. And I don't mean they're shared as in there's some like neat little thing that you run to get between them. I mean that they're the same thing. Then here's the data. So this is actual ATS. All right. So now it's starting to look a lot more like functional programming. And everybody's wondering why we're on, I think, slide like 30. And we're finally at something that looks like functional programming. But here we're declaring a data type. Again, this looks a lot like Haskell. We're declaring all these are enumerated choices. What's all this syntax? So port B of empty parentheses means that this is just going to be a type port B, and you'd refer to it as port B, and it's not going to have any data that's tied to it. Same with C, D, E, and F. So I'm just using it as an enumerated data type. Pound define, pin max 15. Yeah, because, I don't know, people who know something about C just can't get away from these macros. So we're going to bring macros back. You use them a lot less than you do in C, but they are still used. Okay, now this is a refinement type. So this is a little different. What you have here is you say an I is an int such that I is less than pin max. All right, and then this is saying that the sort of I is int. So let's go through that. So first of all, I is an int, so that means it can be a positive or negative integer of whatever the word size of your computer is. And then such that I is less than or equal to pin max. That's a little bit different. So in Haskell, to get something like that, you have to add a plugin called refinement types called Liquid Haskell. I don't know how to do it in Scala, but several other functional programming languages offer refinement types. But that's what you're doing. You're subtyping this. So now you have a type pin that you can refer to, and you know that a pin has to be between 0 and 15. Or actually, in this case, between negative infinity and 15. But you could also add another condition and make it, it has to be greater than or equal to 0 as well. I just didn't put it on this slide. So just one more thing about this. That's a nice property, right? So like now I know that my integer that I'm using can't exceed what I would expect to see for my pins. So I can't accidentally put the wrong, put a pin of 33 in, which if you put a pin of 33 in, it's not like anything bad will probably happen. I mean, assuming you only have 16 pins. If you have more, then something bad could definitely happen, but it can be a really hard bug to track down, honestly, because it could occur anywhere. And you remember one of the things I said about embedded programming, like one of the only tools you have to find things a lot of times is a blinking light. And that can be really rough. So a few more things from SATs. So now we're going to, like I said, this is something that's knowable. SAT stuff is knowable at compile time. So you definitely can know the name of your function at compile time. You can also know the types of arguments it takes. So this one takes a port, which we defined earlier, and a pin, which we defined earlier. So it's setting that pin high, right? So then it's just going to return void because it does that, and then it's done. Another thing you can know, like I said, is an external function call. So here I'm going to call set pin high in C right from here. And again, I have port and pin, and it sets it high. So a lot of times you'll see these like unsafe things being wrapped by this, and then it's just up to you to kind of exclude those when you're trying to make a library for somebody else to use or for yourself to use. Okay, so now we're going to implement the safe version of set pin high. So set pin high is going to take a port and pin and then create a lambda function that takes a port and pin here, and we're going to run that lambda function internal over port and pin and then case match against each possible port, and then set the given pin high. Okay, so what we have here is we know that the port has to be a valid port because we said what all the valid ports are, and we know it has to be a valid pin because we said what the maximum pins are. So those are already guarantees that are starting to outstrip what you'll get in C without a lot of work. And in fact, the guarantee on the pin would be really difficult to implement in something like Haskell because it's so flexible because you can change the size of that pin out easily. All right, so now we're going to get to DATS code here. So this is the blink loop itself. We set the pin high, we run a delay not appearing in this film implementation, and set pin low again. We have port safety, we have pin safety, delay, you might have some like max delay that you'd be allowed to do, and then it just loops. It's a tail call optimized loop, and in fact, recursion can be guaranteed to be tail call optimized in ATS in a process I don't really want to go into because it's really complicated, but tail call optimization is guaranteed. So when you set it up, it'll actually be it'll be a warning if it's not, or an error if it's not. Tail call optimization just means it's able to take the recursion that you're writing and turn it into a simple for loop, which is really, really important if you're trying to write a loop like this that goes on forever. Yeah, so there's going to be like 1,000 features. I'm not going to go in. There's just too many features, but that's one of them. Okay, so views or linear types. Okay, so in ATS, there's an understanding that data is actually stored at addresses. It's not we don't pretend that data just exists out in an ephemeral space and we can just use as much space to hold that data as we want. We actually talk about addresses. An at view is how you say that. An at view says what is stored at a particular address. So some type is at this address. Again, we're connecting types to the machine. This is what's called a linear type, and it's a form of proof. Whenever you use an at view, it's consumed, which means you can only use that at view one time. That's the linear part. That's what makes it linear, is that you can only use that resource once. So when you get a pointer, so this PF stands for some type at L, L being the address and A being the type. So this means that this function is generic. It doesn't know what kind of type it's going to get yet. But this right here is saying we're going to have some pointer L, and then the left side of it is going to say at L, we're going to have some type A. The question mark means that we don't know if A is actually there or not. So we don't know if L is full. So a pointer can be empty or it can have something at the pointer. And in this case, we don't know. So we're telling the compiler, I don't know if we're going to have something there or not. Now notice at the end, after this function runs, it doesn't have the question mark anymore. So what it's saying is that this function has to prove that we go from something that we don't know has memory allocated to something that we do know has memory allocated. That's a powerful idea, and it's one of the ideas that you see a lot in Rust and that they talk about a lot in Rust. The linear types here are similar, only they're more powerful. You can mix them with refinement types. So not only can I say that there's some A here that ends up full here, but I can say that A has to satisfy a set of constraints or properties related to the refinement types or other type system that we have. And you can keep abstracting that out and making very specific views, which we'll get to, some of it. Anyway, here we are actually assigning memory. So I do val unit equals, and then this is my assignment. So notice that this val and then parentheses is then saying to do an assignment. So you can think of this as a statement. And in fact, there's another syntax where you could just write this as a statement. The important part is this part right here. I keep trying to click on it, but the important part is this right here. So we're saying at the address of P, assign a value X, right? So that'd be the same as writing star P equals X if you're writing it in C. And then what we return is the proof function that we had at the beginning, and then unit. But this address of P does the lifting of telling me, okay, well now I know, because you've done this step, I know that this P variable that had that address L is now full, and there's now no question mark because I know that it actually has been assigned. So, I mean, take a minute to kind of reflect on that. Like, we're able to, at static time, know we've assigned a variable of value, or a variable in the sense of like a place in memory, a value. And so from here on out, you can talk about this same value as existing, which is a pretty powerful property. Is everybody with me so far? Good? Okay. All right. I hope everybody who's watching, if there's anybody watching, also feels that way. I don't know if I'm with me. All right, here we go. All right, views plus refinement types. So I mentioned earlier, go away. Go away. Oh no. Oh, I hit the button. I should have hit the button. What was I thinking? This is Lucidchart, by the way. And I've never done a presentation with Lucidchart before. But I really love Lucidchart, so I wanted to try it. You draw a big picture and then you just circle boxes to make your presentation. All right, so views plus refinement types. Like I said, in ATS, all these things are mixable, so you can have the refinement types and the view types and every other kind of type that we have mixed together. So this is a data view, and data view takes a view and an integer, and it creates a constructor that expects a view to come back, right? So here's an example of using it, and then we'll make clear what I'm doing. So what we have in set DDR bit high, you might remember from the first C example I showed that there was a thing called a data direction register. So here we're going to set that data direction register bit high. You pick the value that you want to set high, and this is saying that this has to be known at compile time, the value you want to set high. And when you set it high, it will be guaranteed by the output of this function, which says that this data direction register is at this location and that this pin I has been set high. So this pointer here is actually a pointer to that data direction register. So you're grabbing it and making it where this is the only place that can use that data direction register. Then you're doing some operations on it. So the first thing I'm doing here is I'm getting the value of the data direction register ahead of time, and then I'm setting that bit high, and then I'm assigning this new value back into that data direction register, and then I write this constructor from here, writable, and I put PF in, right? So that says that this proof has been satisfied, and now I can return my pointer. So that's a powerful thing. So now what I have is a statement. This is passable. You can pass this around to other things. I have a statement that says I have something at that pointer who has this bit I written high. That's what I've done here. I've guaranteed that that bit is written high, which means that I can write functions later and know that that data direction register is high. Yeah, so now I'm going to write the most complicated blink loop. All right, so first I run that data direction register, right? So I'm getting my proof that I have access to it. So now I have the data direction register. I put it through the function we kind of worked through earlier. I get my proof back. I'm sorry, I have my writable proof here. And now look, I have set pin high with proof. So this one requires me to prove that the data direction pin that I'm trying to write is actually high. So I'm not showing the implementation details, but that's what we're getting. So it's requiring that the pin I want to write to has been set to be a writable pin, which is a really interesting guarantee. And then delay. Delay is the one that I feel like looks the most similar to the original delay. And then again, set pin low with proof. Again, I have to prove that the function, that the data direction register is high. So I can prove that, and then I run delay, and then I loop again. So round and round we go, blinking our lights, just like you see. Yes?
So those proofs and everything, are those purely at compile time? Is there anything that...
Yeah, they're completely erased at runtime. Complete erasure, yeah. That's a great question. Let's see. One piece that isn't as erased as I wanted it to be, and it's probably a good way of doing it, is the pointer. If you'll notice, I have to pass that DDR pointer around. That's just to hold on to that resource so that you're saying, I am the only thing that has this resource. That, I would like to figure out a way to not do that, and I'm pretty sure that there is. I just don't know it. Okay, that's all I have in terms of slides. Let's see. There's a little bit of time left for questions and stuff.
So for those things that you do have to put on the stack there, is ATS like cognizant of like what you're trying to put this on and how much stack space you're using, that you're not going to like overrun memory?
So he asked if ATS is cognizant of how much stack space you're using. So you can do variable assignment and explicitly do stack guarantees or heap guarantees. But you're usually using C to do the heavy lifting there. And I'll show you a little bit of the make file, actually. Let me see if I can switch my view here to make it where it shows my other screen. Can I do it? Oh, sure, yeah. That's a great question. Yeah. Hold on. Let me. How do I do that? Let's see. I'm gonna just hit buttons until something happens. Isn't this a fun way of spending some time? Hold on. Okay, I'll just try dragging it over there and just looking at it while I'm doing it. Let's see, I drag this way. And then, oh my gosh. Oh no. So let's see, that's programs, ATS. So this is the Arduino make file. So I can show you the make file first really fast if there'd be interest in seeing that. Yeah, that circuit playground's Arduino. So this is the make file that it's using. So you can see like I'm just this is like normal AVRC stuff. And then here we have, he has to grab all the cats files, DATS files, DATS, all that stuff.
So you have to split those out, the sats, the DATS, the hats, and the cats every time.
Yeah, you wouldn't have to do it if you weren't trying to do embedded, but with the embedded stuff, because there's so much, what he asked is you have to split sats, DATS, cats, and hats out. So hats, first of all, I don't even know if I had it up there. I like never use it, so I don't ever use hats. I'm sure that there's a really good reason to use hats. I don't know what it is. The DATS code, if you're writing on your desktop, that's all I ever use. I never use sats files. But when I'm writing code where I have multiple things depending on C things and one part of the ATS depending on the other part of an ATS code, and that's all happening in the embedded where I'm using make files, then I'll use the sats codes because it's a lot easier to write the make file. I think there's a way to do it without doing that. It's just you'd have to have a more complicated make file to put it all together correctly and link it correctly. And that's really what I don't know how to do correctly. So I did it like this. Yeah. And this was enough. So,
Very few languages I can think of where you could say, it's just easier to use a make file.
huh?
There's very few languages I can think of where you hear somebody say, it's just a lot easier to write a make
Oh,
file.
yeah. Well, this is that one. This is that case, for sure. But, yeah, so like we're just composing a bunch of stuff. I don't know. I'm wasting time here. Let me show you. Let me see if I can find some of the C code that's being generated. This would be easier if I could see it on my computer, but here we go. Let's see. There's my build. There's my EEPS. There's my assembly. So this is the final product. So I probably can't find it here, but I can probably show it to you not in that, but in the, So, and I'll post these repos, but I have this repo, and this is everything that I'm doing to learn ATS. So I have all kinds of nice examples, like things that are really important, like how you correctly write sorts. So these are all the different sorts, and yeah, there's a lot of sorts, and a lot of this. Theorem proving examples. These are how you do theorems. Yeah, so there's a lot of theorems you can do. Anyway, let me find some code. Target. My examples. Oh, no. Okay, well, it's not spitting out code because I think I'm just having it run the packages directly, so it's not spitting out the C code, so probably not going to be able to do that. But the C code looks good. I mean, it's not not super verbose C code. Yeah, I don't know. That's one thing that you should probably see is one of the more frustrating things is like how easy stuff is really hard, like stuff that should be easy, like for instance converting a double to a float. This is the function you use to convert a double to a float. Like I said, research programming language. Welcome to research programming languages. They don't care that it's not easy for you to use. So, hopefully you understand that like it's just interesting, a lot of interesting ideas. Anyway, anything else?
You've been using this for 2 years?
Yeah, but not really heavily. Not really heavily.
So it's got an extreme hipster quotient, and like if you go back 2 years ago, you may have said not so much, but Rust was a little bit hipster, but now everybody seems to know and use it, and it seemed to get you like 80% of the way there.
Yeah.
Have you thought about using Rust for embedded?
My biggest problems with Rust are, first of all, it's not very functional. It's not a very functional programming language. I'm sorry, I shouldn't say my biggest problems with Rust. I love Rust. Like Rust is a great thing. I think it's so cool that Mozilla is sponsoring it, and I really don't have anything terrible to say about it. Personally, I like to have a little bit more expressiveness in my type system than Rust is willing to give you. ATS gives you that, the operability with C and the memory management that you get in ATS is more than what you get in Rust. Plus, the details of linear proofs and the linear type system are more exposed in ATS than they are in Rust. In Rust, you have a thing called a linear type, but having these like composed types like this, it's just not a possibility that, at least that I know of. But no means claiming to be a Rust expert. So if somebody knows how to do, some of that stuff, I would be really interested. But if I were going to pick a language to try and do an embedded project in, I would definitely pick Rust right now. I think this is what it could be, and a way for functional programming to play in the space. There's some really interesting things like I think the termination guarantees, for instance, the fact that you can guarantee functions terminate is really interesting, and I don't think Rust has anything like that.
Use Haskell for other things?
Yeah, so I work at Plow Technologies. Everything we do is in Haskell or OCaml.
You probably said that at the beginning.
No, I didn't. Yeah. But yeah, we're a full functional programming shop, so everything we do is in Haskell, OCaml, Reason, functional stuff. I've been having to write too much Python lately. I'm not a big fan. What were you going to say?
So you said that the refinement types are actually checked at compile time?
Yes. So he asked if the refinement types are checked at compile time, and yes, they are.
So what kind of things can you actually check for? It seems pretty important.
Yeah, so he asked what kind of things can you check for. So the requirement is that the things have to be linear. And it means like a linear logic definition of linear. So you can have things like, here, I actually have some examples. Maybe. Yeah, so this is using refinement types to check that there's a multiplicative property called isTotal. Yeah, that's kind of hard to walk through because I can't see it. Hold on, let me find one that's simpler. This is not simpler. This is more complicated. There we go. I think this is the one that I did some stuff that's interesting. Yeah, so here's some examples of stuff you can write at compile time. a nat, let me make this bigger. Oh, that's smaller. Bigger. So here we have a definition of a natural number, right? A is greater than or equal to 0. Definition of a positive number, negative number. Alternate definition of a natural number. You can carve out sets. So here we have, a natural number that's 0, 1, aka a bit. Then here we have one that's just between these values. So these are all properties that you can do. And then, like I said, you have a theorem prover. So you can compose the refinement types with theorem proving to prove nonlinear things. So like that multiplicative identity is provable, even though that's a nonlinear thing, because multiplication of two variables is nonlinear. You can still prove it because you use a theorem prover instead of the refinement types. You can also use external theorem provers in ATS if you just don't have enough theorem proving. You can tie in Z3 and SMT solvers, and that's fun. I've never done that. Yeah, but you can define these different types sort of separately, right? So you can type def nat, and now you don't have to keep writing this big expression over and over. You can just write nat.
So does that have to be constants that go in there so that it knows where it is at compile time?
It has to be things that it can figure out at compile time. Yeah. So either constants or sets of constants that compose to make nats. So if you have a 3 and a 5 and a 7 and you have a function that adds those numbers, then it knows that that's going to be a positive number, and it'll be fine.
So you can't take a number pad number and stick it in there again.
Yeah, no, but you can say things about that. So like the way that you deal with that is what you can do is you can write a little bit of stub code, and then you can say in your stub code, so what he asked is you can't just take a random number and just make sure that it works. But what you can do is say you're deserializing from a file, right? So you deserialize your code from a file and you get the number 37. So what you do is you say input from file, check and see. If this number is, less than 0, then return an error of some sort. If it's greater than 0, now you know you have a nat, and so now you can proceed as though you had a nat in the first place. So what you've done there is you've moved an error that could be anywhere to an error that's localized in a place you know where to look for it. Exactly, it's kind of like sanitization is what he said. Yeah, and then you can do stuff with arrays and stuff too. So this is string is at an end. These are just examples taken from the ATS book. So yeah, I don't really want to go into all that. I'd have to really think about it. Does anybody else have anything? All right, thank you very much.